Hi, this is lecture number 2, and in this lecture we're talking about the basics of modeling. How do we begin to model systems? So if you remember the promises we had at the beginning of this course, one of the three objectives is to develop a math model for any given linear system. So that's what we're talking about here. And chapter 2 in the lecture notes talk a little bit about modeling, one aspect of it. In terms of models, we have models based on analytical results or empirical results. Analytical is based on theory. So, for example, you may have the laws of physics, for example, Newton's laws or Kirchhoff's voltage laws and so forth. Those laws define the behavior of a system. Okay, we can also have empirical models based on experiment data. So they kind of go back and forth, because how did the laws get invented in the beginning? Well, people started doing experiments and noticed these relationships, and that's how the laws developed. So in a sense, the laws really are an application of the empirical and vice versa. We can have parametric models or non-parametric models. A parametric model is a model where you know the parameters of the system. So for example, whenever you define anything using analytical method, you have parameters. For example, a circuit, you have a resistance value. That parameter R that's a parameter. So any of the values, RLC, all of those are values, and they're parametric values. We can also have non-parametric model. So for example, a Bode plot is a non-parametric model. You can actually obtain a non-parametric model without actually knowing the system differential equations at all. So when it comes to passive elements, there are 4 essential passive elements that we would work with. So these are the 4 elements. We have a resistor, capacitor, inductor, and memristor. A memristor you don't hear too much about yet. We will probably be hearing about them more in the future. And we have these different relationships between them, for example, voltage and current, flux linkage, that's the lambda, and charge. So for example, in a capacitor, we have charge that we have. So we have all of these different relationships. So for these 4 components, we have these: V is equal to IR, V is equal to L di dt, I is equal to C dV dt, and then d lambda dt is equal to m dq dt. Actually, this equation is actually the same as that, where m is equal to r, because d lambda dt is actually voltage, and dq dt is actually current. So very similar relationships here. So these two, memristor and resistor, are actually very similar to one another. So these are the basic components that we have for modeling passive circuits. So in general, the interconnections are obviously very important. KVL and KCL equations must be written. A KCL equation must be written for every capacitor. A KVL equation must be written for every inductor. You can write the KVL and KCL equations either in differential equation form or impedance form. So using impedance is another way of working with circuit components. So let's take a look at an example. Here's a circuit, two capacitor circuit. I can write a KCL equation at this node, V1. And so in this case, I would write the sum of the currents leaving the node is equal to 0. So here, 0 is equal to the sum of the currents leaving the node. So from that node, from here to here, the voltage drop is V1 minus Vin divided by R. The voltage drop here is just V1, so the current through here is C dV dt. The current through here is V1 minus V out divided by R. And so that's the expression for the current leaving that node. Then if we look at this node, we have this set of equations. So in this case, we only have 2 capacitors. We don't have any inductors, so we need a KCL equation for every capacitor, and so we don't need any KVL equations in this case. So we have this equation, So the current through here, notice it's just equal and opposite what we had in the previous equation. And then we have C dV dt here as well. So those are all of the equations. Now I can manipulate these equations by taking the Laplace transform, using the differentiation property of the Laplace transform to take the Laplace transform of this equation, and I can solve for this relationship between V1 and V out. I also have another relationship between V in all of this, and so I can go through and solve for the relationship V out over V in, and in this case this is the form that I get using Laplace transforms. Or if I want to have a monic denominator, I would have it in this form. So I can actually get a transfer function, and that's one model. In this case, this is the parametric model for the system. So the parameters are the R's and the C's, and we get a model. So using all the circuit equation knowledge that we have obtained from various previous classes, we can create a model for a circuit, just like this circuit we did here. Now, notice we've only used passive components, R, L's, and C's. We could have used M's, that is the memristor. But we didn't use transistors, we didn't use diodes, which are nonlinear, which have a nonlinear characteristic. Okay, so at this stage, we're keeping everything essentially linear. Not totally linear, but essentially linear. The next circuit component we have is an op-amp circuit. So the op-amp is an important circuit. So the op-amp essentially has what is called a high impedance input. And that high impedance input has several ramifications. One of the ramifications is that since it's high impedance, there's no current flowing through this device. And since there's no current flowing through there, these two voltages are essentially the same. Okay, so this is considered a virtual ground for this circuit because this is essentially ground since there's no current flowing through here. And so it's not really connected to ground, but it's virtually ground. So essentially this is a ground value. And so you can go through and analyze this circuit. And so if this is ground, then the current through this leg here is U1 over Z1, the impedance Z1. This current is U2 over the impedance Z2. This is U3 over the impedance Z3. And so that's what each of these currents are. Notice that no current can flow this way, so all of these currents must flow this way. IF then is the sum of those currents. Okay, and so then I can apply this equation. Y is equal to minus, so notice it's going the opposite direction, minus ZF times IF. Okay, and so that is how we would analyze an op-amp circuit. We could take the Laplace transform and we can see that Y then is a function of the three inputs. Okay, and so notice ZF appears in each of these three expressions, and Z, the individual's input, Z inputs, appear in the denominator. So what is Z? Well, Z is an impedance. Z can be an R, an L, a C, or a combination thereof. And so depending on what we choose, we can get different kinds of circuits appearing. So if we now restrict ourselves to a single feedback element and then an input element, then we would have these possibilities. Okay, so we have the input component Zi, the feedback component ZF, and we get a transfer function. Okay, so in this case, if I have resistors, the transfer function is just a constant gain inverted. So notice there's a negative sign. So if the resistors are equal, then we get a gain of -1. Okay, so that we always get a negative sign because of the fact that we actually have this input coming into the negative terminal of the op-amp. And it turns out that this negative terminal is really important because we're actually applying feedback here, and negative feedback is really the way to keep things stable. So that's important that we have it that way. Okay, so the next case we have an R and a C, in which case we have -1 over RC times 1 over S. So this gives us an inverting integrator. So the inverting is the negative sign, the integrator is a 1 over s. If you look at the integration property of the Laplace transform, the Laplace transform tells us that if we take the Laplace transform of the integral of a signal, we get 1 over s times the Laplace transform of the signal. So the integrator acts like a 1 over s in terms of transfer functions. Okay, and it's very common for c to equal 1 over r, in which case rc is just 1, and all of this just becomes minus 1 over s. So that's a common way of doing it. So this gives us an integrator. So we have an r and a c. If we swap the two, okay, notice instead of having, we basically get the inverse of the reciprocal of this, not the inverse, the reciprocal, minus RCS. So this is a differentiator. Okay, again, it's common for r to equal 1 over c. But now, here we have a differentiator. Now, differentiator turns out to be not a particularly good way of implementing circuits. It turns out that differentiators tend to be very noisy because of the way they amplify high-frequency signals. So they tend to be very noisy. And if you have any high-frequency noise, it amplifies it, and that's not a good thing. Well, so here now we have a resistor in the input, and then RC in the feedback, parallel RC in the feedback. This is the transfer function we get. We have a single real pole located at minus 1 over R2C, and it has a DC gain of minus R2 over R1. So we have a single pole. Okay, so if we apply it that way, so one capacitor gives us a single pole. Okay, if we have instead of it parallel, if we have a series connection, then notice we get S plus something over S. So this is like a PI controller. So when we study PI controllers, this is one way of implementing a PI controller. So notice I get a 0 over S. Okay. Here, this connection, I have a parallel combination RC and then another resistor in feedback. So notice I get S plus 1 over R1C. So this is like a PD controller, proportional digital controller. Okay, so we talk about those in EE 314. And this is how we could actually create a circuit that implements those things. Next, we have two capacitors, two RC parallel combinations, and this is what we get. Notice notice we get a pole and a 0, a single pole, single 0. So this we're using two capacitors, but we still only get one pole, but we get a 0, not at the origin. So this is the op-amp circuit that way. So this is a standard way of doing things, and it turns out you can interconnect stages like this to create an arbitrary transfer function. Okay, in fact, the connection of stages like that to form an arbitrary transfer function is the basis of what is called the analog computer. So most students are familiar with the digital computer because that's the kind of computer you're using right now to watch these kind of lectures. So digital computers are well known. Analog computers not so well known. But it turns out that the analog computer was really the computer that put man on the moon. They talk about how the digital computer that put man on the moon was, your cell phone is like 100 times more complicated than that digital computer that put man on the moon, and in fact it is. But it's not really the digital computer that put man on the moon, it's the analog computer. The analog computer is a connection of R's and C's and op-amps and things like that that can be used to simulate the differential equations and the kinds of trajectories that they needed to be able to do the moon trajectories and so forth. So op-amp circuits are very useful that way. And so these are some of the basic uses for a single stage of op-amps like this. The next type of single stage op-amp circuits use something called a Sallen-Key circuit, and there are three possibilities for this. We can have a low pass characteristic, a band pass characteristic, or a high pass characteristic. Notice that the high pass and the low pass are very similar to one another, with the R's and the C's switched. Okay, here's the transfer function that we get for for this circuit. Okay, so this is like your standard second order prototype. It can be implemented using 2 R's and 2 C's. So here omega naught is given by this expression. Zeta here, notice that I've thrown in an omega naught here. And so by appropriate choice of R1, R2, C1, and Z2, we can get a standard second order transfer function here. Okay, so the value of this is that we can actually get complex poles. So when we have the first order systems like we showed before, you only get a real pole. You don't get complex poles. So here we can actually get complex poles. So this is more general. For the bandpass, again, we get complex poles. Notice that we have a 0 at the origin. Okay, and so this gives us something that's like what's called a rooftop filter. So at zero frequency, and then it goes up, and then it breaks down at omega c. Okay, so this is a bandpass type filter, and then this is a high pass type filter. Okay, and so notice here omega c is not the same as omega o. Notice that this omega o is the same in both cases, but the omega c is not the same. The alpha and zetas are not the same as any of these circuits. So for example, these two zetas are different from one another. And I didn't even give you the formulas for this because this is like way more complicated. So notice this not only has 2 R's, it has 5 R's altogether and 2 C's. So this is a lot more complicated than these two. You can look this circuit up in various places. Even Wikipedia has a nice page on the Sallen-Key circuits. So we can create circuits with transfer functions using op-amps in various configurations. And by connecting them together, we can get as large of an order transfer function as we want. Okay, mechanical systems. We have a number of components. So we've looked at electrical systems, including the passive components. We also have mechanical systems that we can look at. So a mass, a spring, and a damper are the basic mechanical types of components that we would use. So the mass satisfies Newton's law, right? Force is equal to mass times acceleration. That's what we have here. A spring satisfies Hooke's law. So the force is proportional to the stretch of the spring, x1 minus x2. The damper has a similar relationship. We have some constant times of the difference in velocity between the two ends. The difference in velocity. Okay, so these are the basic mechanical components. There's actually a lot of similarity between these basic mechanical components and the electrical components that we've shown you, the passive electrical components. So we can now, with mechanical systems, we can write mechanical equations, okay, which are basically all Newton's laws equations. Sum of the mass times acceleration is equal to the sum of the forces. Okay, so we notice here in this first mass times the acceleration, that should say x2, that should say x3. Sorry about that. So this force, x on mass 1, I have a spring that acts on both mass 1 and mass 2, but notice that its force is proportional to the stretch of the spring. And then here I have a friction. So notice the friction only is associated with position x1. And then I have similar equations for masses 2 and mass 3. Notice between mass 2 and mass 3, I have a damper. And so notice that this spring force between mass 1 and mass 2, notice here I have x1 minus x2. In the next equation, I have it reversed, x2 minus x1. Similarly, this damper, I have x2 dot minus x3 dot, and notice it's reversed here, equal and opposite. Okay, so these are the kinds of equations we get. So now we could, for example, get the transfer function from the input f to the position, that should say x3. Okay, oh, there, that's better. Okay, yeah, now I fix those guys. Okay, So these are the equations then, and we can get a transfer function, for example, from the input force to x3, for example, or x2 to any of these signals. So these are the kinds of things we can do, and we can get transfer functions, models, for systems like this. So this is using the analytical method. We talked about this in EE 314. I'm just reviewing this for those who perhaps have not seen this in EE 314. So for rotational mechanical systems, we have torques and rotational angles. And so we have, this is Newton's law for rotation. So we have the torque is equal to the inertia times the rotational acceleration. For a spring, we have that the torque is proportional to the twist. Okay, so if you have a spring that twists, then the torque is proportional to the twist. Similarly, for a damper, we have that the torque is proportional to the speed of the difference in the speeds between the two sides. So we have rotational mechanical systems with those characteristics. Here we have a permanent magnet DC motor, which is an electromechanical system. It has an electrical part and it has a mechanical part. So we have an electrical equation. So notice this is basically a KVL equation. Notice that we have an inductor, so we need a KVL equation with that inductor. So here's our KVL equation. This has the voltage is equal to the current through the resistor, the voltage across the resistor. Here's the voltage across the inductor. And then we have what's called the back EMF. Okay, the back EMF is basically the voltage that is responsible for making a DC motor into a generator. That is, if we actually turn this thing, it will generate voltage across here. And so that voltage is proportional to the speed of the motor. So this is the electrical equation, and notice that it has a mechanical term involving the mechanical speed. Here's the mechanical equation. Notice that it has an electrical component. That is, the inertia times the rotational acceleration is equal to these terms. So notice I have this damping, which is proportional to the speed. And then this term is proportional to the current. So KT is the torque constant of the motor. And so this is the torque that's generated by the electrical windings and so forth. And then we in general might have a load torque, that is, there may be something else that's added onto here. So this is the equation for a permanent magnet DC motor. And so we can do electrical, mechanical, electromechanical. So these are some of those things. By way of example of putting some of these things together, the NASA has a system called the Advanced Reduced Gravity Offloading System, the ACTIV, sorry. So the A stands for active. And so here, notice that it's basically uses a cable and a winch to support the guy's mass. And so he's able to be as if he were in reduced gravity environment. So he can practice running, he can practice all kinds of things in this reduced gravity environment. Practice walking. It's actually not that easy to walk that way in a like for example, moon gravity. It's not easy to walk that way. So this is showing him walking up an incline, going up an incline. So basically we have a winch up here, winch system that is supporting the guy's mass. And so we have this mechanical thing in order just to brace it. But basically it's just a cable attaching this mass. Okay, so it basically has a simplified model that looks like this. We have a winch, which is basically a motor with a cable and a mass. Okay, so we can easily model this as a system. We have a motor system here, and attached to it is something that creates a torque on this motor, and that is this mass. Okay, and so if you think in terms of there being a force here creating a torque on this, the torque is equal to the force times the radius, or the distance from the center out to that point. So we can easily model a system like this. It's fairly straightforward. So it's actually cool to see a practical application of this. And so that's the ARGOS system. In addition to having a parametric model, which is what we've been talking up to this point, we can also get a non-parametric model from empirical data. So by way of empirical data, we know that the frequency response of a system involves applying a sinusoid of a given frequency omega. The output of the system is also a sinusoid of frequency omega, different magnitude, different phase, same frequency. Okay, so notice that the frequency here, that the magnitude here is a function of the frequency. The phase is also a function of the frequency, and we can plot, for example, the magnitude versus frequency and the phase versus frequency, and this combination of plots actually gives us the Bode plot for the transfer function of the system. Okay, so this Bode plot is actually a model. It's a non-parametric model because if all we have here is this data, like this doesn't tell us anything specifically about where the poles or zeros are or gains, and so it doesn't give you a transfer function directly, but you can work to find a transfer function that fits this curve using various curve fitting type techniques. But this is a non-parametric model that we can obtain for a system. Okay, so this is the basics of modeling. Thanks for watching.